In this video, we'll be demonstrating how to implement remedial measures in simple linear regression in R. We'll be talking about three different types of transformations that we can use. One that's an easy transition, one that's hard and actually impossible, we'll see, or not possible with a reasonable number of transformations, and one where no transformation is needed. For the first example, we'll be using the trees dataset and assessing the volume as a function of height. Looking at a plot, we can see that as the height increases, the volume roughly increases. But one thing that we can notice even from a raw scatter plot is that the variability at low heights is different than the variability at large heights. We can plot a residual plot using the plot function for our model. Now, we haven't talked about this too much, but when we use a plot function for our model, we have multiple different options that we can select, which are diagnostic plots for assessing the assumptions within that model. I'm just going to choose the first diagnostic plot, which is the residual plot, and works a little quicker than making it by hand. Sometimes, though, it's important to realize that using the built-in default plots have some things that we don't need, such as this red line. So I might not choose to include this in my report if I were writing this up for real, because the red line would be a distracting feature about this plot that actually isn't part of my assessment of the residuals. What I can see from the residual plot is that it echoes my initial observation that the residuals are relatively narrow on the left side and relatively wider on the right-hand side. This could just be a fluke, so I might run the statistical test to check it out. Looking at the statistical test, the Broche-Pagan, it seems that this is a statistically significant effect where my homogeneity variance, or homoscedasticity, has been violated. To finish out checking my assumptions, I'm going to look at the normality plot, and I see that this looks relatively good. Looking at the initial plot of this data, I can see that not only does the variability tend to increase, but it seems like this might have a bit of a positive slope or a nonlinear relationship. Because of this, I might think of the square root transformation. So I'm going to give that a shot. I'm going to make a new variable called sqrt_vol for the square root of the volume, and in that take the square root of the volume of the trees. Then I'm going to plot the square root by height to see if it looks visually a little bit better, and for me it does. It appears that the linearity issue, that peak up, looks a little bit better. It also looks like the residuals got a bit wider on the left-hand side and stayed a little bit narrower on the right-hand side. So this looks like it could be a good option. So I'll go ahead and fit my model, and then I have to recheck all of my assumptions, not just the one that I was trying to fit. My residual plot does look quite a bit better than the initial one. That is, it looks a little wider on the left and it looks a little narrower on the right, but it still looks like there's some work to be done. It looks like it's slightly wider on the right-hand side than on the left-hand side. I'll run a statistical test to check this, and what I see is that though the p-value decreased, it's still statistically significant. Now, taken with the plot to be 100% honest, I could look at this plot and very easily say there's not that big of an issue. The other thing is that I know that volume is a function of height just in general, and that the volume and height relationship is much closer to a squared relationship than it is to a linear relationship. So it would make sense to me that taking the square root of volume would be closer to height, though I know that the relationship between volume and height isn't a squared relationship, right? But it is closer to what that actual relationship would be. In this case, though, I'm going to continue to look for options just to see if there's anything better out there. Now, don't forget that when I do a transformation, I need to double check my assumptions again. And actually, I can see that normality looks like it got a bit thrown off. I've got a little bit of a wiggle in the middle of this data set. The ends look relatively good, but it almost seems to have that lazy S shape a little bit. It doesn't appear too bad, but it is something that I want to keep an eye on. I would call this a borderline normality plot and could check it against a variety of other plots if I wanted to make sure. Now I'm going to check in with boxcox. The boxcox command, lowercase b, uppercase c, is from the car package, so I'll just call the car package to load this in. In the boxcox, I see a distribution of the log likelihood for different lambdas. We want the log likelihood to be as as high as possible. Now this is kind of opposite of sometimes what you see. Very often we look at -2 times the log likelihood in fancier models, but in this case we want it to be the smallest negative number possible. So here I'm looking, I see lambda has a reasonable value from about just under +1/2 to just over -1/2. And I'm looking again, not the middle lambda, which might be -0.15 or something like that, but I'm looking for a lambda within this confidence interval, the 95% confidence interval, from this outside edge on the right to the outside edge on the left, and trying to find a lambda that's a nice number or convenient number. One that immediately jumps out to me that's actually pretty close to the guess is lambda equals 0. Another one that's a good possibility is lambda equals -0.5. Both of these are numbers that we included in our slide. So I'm going to start with lambda equals 0 because it looks like it's a little bit closer to this guess than lambda equals -0.5 to me, but both are options. Note too that square root is just on the outside of our confidence interval. So square root we're not going to treat as an option from our box-cox traditionally, but it does make sense, and again it is a bit supported by theory. So this square root transformation of y might make a little sense. Another one that is also something is the cubed root transformation, and that's one that we could consider as well, though we won't in this example. Now for the log, that is lambda equals 0, recall that that suggests the log transformation of y, so I'm going to use the log of the y variable and then include that as my new variable. Plotting, I see that this also looks like it fixed the linearity issue, and actually this looks like it's got a decent spread on the residuals as well, so this might look pretty good. Looking at the residual plot, yes, the residuals definitely look well spread out on the left and the right here, so this certainly visually appears to have fixed the residual issue. Looking at the statistical test agrees. There is no statistically significant challenge to the homoscedasticity assumption in this case. We'll follow up with a look at normality, and in this case we again see this little lazy S shape peeking out, so normality might be an issue that we fixed homogeneity of variance using this transformation, but the normality looks a little bit worse. Comparing my square root model normality to the model normality from the log transformation, it looks like the log transformation, it's got these little points here which throw it a little bit further off than the square root, which kind of plugs down or is a little bit smoother. So I'd say the log transformation is a little bit worse in terms of normality than the square root transformation comparing these, though the log transformation is a little bit better in terms of the homogeneity of variance. Looking at our box-cox, recall that the other option that was considered was a lambda equals -0.5 option. So that is the inverse square root transformation. So that's just y to the -1.5 power. The 0.5 means square root. The negative means 1 divided by. So that's why, or inverse. So that's why we get the inverse square root. And it really is just 1 divided by the square root of the y values. I use that as my new y, and I see that the inverse actually changed the direction of the plot. Now this does look reasonably linear, maybe with a little curve here, but reasonably linear. So I'll go on and fit the model. I'll look at the residuals. The residuals actually look better. They look fine. There's a decent spread on the left and on the right, so the residuals I'm actually pretty comfortable with this transformation. It's a bit of a tough transformation in terms of interpretability because there's so much going on, but it seems to have fixed the problem, and the statistical test agrees. In fact, the p-value is even higher than it was with the log transformation. Checking out the normality assumption, one nice thing about this transformation, there might be a little bit of a lazy S shape here, but certainly in comparison to the natural log, it is much better. So this distribution or this transformation, the inverse square root transformation, also seems to have done a better job in terms of fixing normality. So now we need to determine which is best overall to go with our interpretation. We tried 3, the square root, the natural log, and the inverse square root transformation. For me, I think the inverse square root transformation, it fixed our homogeneity of variance, and comparing the normality plot to the square root normality plot. So back and forth, this is the inverse square root. This is the square root. Again, that square root has that s that keeps throwing me off. This has it a little bit, but it seems much, much better. And then comparing with that natural log and the inverse square root. Yeah, this has those points. I really don't like those points, making that a really sharp looking S shape versus this inverse square root, which has a little bit of deviation, but it seems relatively mild in comparison to those others. It really does look like the inverse square root for this data is the best transformation. Not because of the homogeneity of variance. All three of these address it. The square root addresses it the least. The natural log addresses it better than the square root, such that we don't have a statistically significant violation, and the square root addresses it even better than that. But I would pick the inverse square root because of the three options, it is the one that least impacts my normality assumption. So I'm going to go on and look at this model, look at the summary, and then the confidence intervals for the different parameters. So this is what I'm going to interpret. Use Control L to clear out there. Okay. So now for interpretation, we can look at significance, and this is important. I can say that my height is a statistically significant predictor. But what does this mean? Is height positively related to volume? How can you even tell? And this, my friends, is the hardest part. This is the reason that I hate transformations, is because what on earth does this number mean? What does even a positive and a negative number mean when we're performing these types of transformations? How could I possibly interpret this? Well, the statistical interpretation adds a little bit of complexity, but honestly, the statistical interpretation is really easy. For a single unit increase in height, the inverse square root of volume decreases by 0.005, and a reasonable range for that decrease would be between 0.007 and 0.003, again for every unit increase in height. This decrease in volume decrease in inverse square root volume per increase in height is statistically significant at the alpha equals 0.05 level. It's statistically significant at the alpha equals 0.01 level. It's statistically significant at the alpha equals 0.001 level. So it's a statistically significant effect. We know that this there's reason to believe that this value is not zero. There's evidence to claim that in the population. But okay, that's our statistical interpretations. What's the practical interpretation? Is this large? Is this small? How does height relate to volume? The question, as it was asked, was not about height's relationship to the inverse square root of volume. The question was about height's relationship with volume. The only reason we're using this inverse square root junk is to try to fix our assumptions. And in fixing our statistical assumptions, what we've lost in a very meaningful and important way is interpretability on the whole question we were asked in the first place. Let me say this in a different way. If my boss handed me a problem, I'm working for a tree logging company, and I was given a problem to find the relationship between height and volume. And so in running my statistical model, I found all of the errors or all of the violations of assumptions that we have observed today, and came up with this model and went back to them and told my boss, well, the inverse square root of volume is negatively related to height. And I kind of stuck up my nose a little bit and felt very, very proud that I found this. My boss would laugh me out of his office because that is not what my boss cares about. What my boss cares about is how is volume related to height. So how can you possibly look at this and come up with that determination? Well, it is possible. It's a bit painful. What we have to do is undo the transformation. So we have to do the opposite of this transformation. Think about what we did in our notes where we undid the squared transformation of y. We have to do something similar here, but it still has an impact throughout the other components of the model. So it's important to realize that even in doing that, that doesn't completely fix our issue. One thing that we can do is we can use some functions in R, like some functions in R. I suppose I should save my juice here so we can talk about them later. But we can do that to predict the different values. So what we'd use is the predict versus the fitted function in R to come up with a few predicted values. And what I would do, so we could do predict and fitted, but the problem is that predict and fitted are both going to give values on this particular scale. If we used a generalized linear model, we could actually use the fitted function in R. It's just like predict, but fitted would undo this transformation if we used a generalized linear model. But here we're not. We're using a transformation. So what we'd have to do is by hand predict a few values for the volume using height, and then we would have to by hand undo the function in R, again demonstrated in our notes, to get a couple of predicted values for the volume for a few different heights. So I'd come up with a table. Here's, a few different heights. One of the ways that I could do this is take a summary to find some good height values that I should select. So summary, trees height. So maybe I'd pick the minimum height, the first quartile, the median, the third quartile, and the max, my 5-number summary, and then predict heights or predict volumes of trees for each one of these heights, and then go and hand that to my boss and say, well, these are the expected volumes that we would have in each of these heights. And the reason is because this transformation really makes it impossible to interpret the nature of the relationship between height and volume directly. Again, we demonstrated earlier how we can statistically, quote unquote, interpret this relationship between height and the inverse square root of volume, but literally no one cares. Nobody cares about the relationship between height and the inverse square root of volume. Now, what is this useful for? I can lean on these statistical significance. I can say with pretty good confidence that height is related to the underlying volume. The problem is that the transformations make the nature of the relationship between height and volume difficult to look at. One of the best ways I can do that is to just go to my original graphic, and what I see is that as height goes up, volume increases. This is really important. I mean, this is kind of a no-duh common sense. Well, if a tree is taller, it has a higher volume uh, of wood or a higher volume associated with it. But this is negative, and that comes from our inverse. So you can't even trust the sign with certain transformations. You really just have to lean on the statistical significance and say, yes, it's statistically significantly related, and then do a few predictions and do the inverse transformation, undoing all the work that you did here to get the transformation so that you can, for the predicted values, so that you can get a couple of predicted values on the scale of volume and walk back with that. So this illustrates how we can try a few different options. We found one that actually worked pretty well. This inverse square root did work pretty well at fixing those issues. But what we find is that even though the transformation worked well, we had some other major issues pop up in terms of interpreting this after we're all done. So again, lean on the statistical significance interpretation. That's fine, and that's what we're trying to study, is the relationship between height and weight, and is it meaningful? What you should not lean on is the parameter estimates. Now, there are some cases, let's say you just did like a square root transformation, where we could feel a little bit more confident at least about the sign of this, or a log transformation. But in an inverse square root, we can actually see that the sign has changed because of the transformation. So we really have to lean on doing a few predictions for our height values to get to this inverse square root. In fact, this is important enough that maybe what I'll do right now is I'll just go through a particular case and demonstrate predicting volume using height in a transformed model. And so what I'm going to do is I'm going to have pH, which is a few predicted height values, or height values for which I want to predict the volume. And I'm just going to copy these over from my notes there. And then I'm going to have PTY, the predicted transformed y. And so I'm going to predict the inverse square root model. And recall that I have to give new data as a data frame. And this is going to be height is going to equal my pH values. Oh, and I didn't enter that yet. Oh, height. I misspelled. There we go. Okay, so my predicted transformed y values, these are the inverse square root of the y values. So inverse square root. So I have to undo the inverse. So 1 divided by undoes the inverse, and I have to undo the square root. So undoing the square root, that's a squared. So I take 1 divided by this value squared. So a couple of predicted height values are going to be 13, 20, 24, 31, and 50. Now what I'm going to do here to make sure that this makes sense is I'm actually going to pull in my original plot. So here's my original plot of my data. And then I'm actually going to add these points to the plot and make sure that they are reasonable points for which I should have. So these are my new, I'll call them PY, because these are actually my predicted Ys after being transformed. So you can either do this using points or lines, depending on if you just want to put a single point here. If you kind of want to connect them in a line, I'll connect them in a pretty line. So pH is going to be my X values, PY is going to be my Y values. I'll make the line width a little thicker, and I'll make the line color red. And I'll really hope that this works. And I see that actually this does look like it's reasonable predicted values for Y. And actually I'll make the type equal to, nope, lowercase b, so that it has little dots on it at those specific predicted values. So these are the specific predicted values that I'm drawing this out for. And again, what am I doing here? Well, I did my prediction, I did my reverse transformation. So come up with predicted Y's on the same scale as the original Y through reverse transformation. And what I actually may hand my boss is I'd make this a nicer table, but I'd make a little table of the predicted heights and then the predicted volumes, and just walk to my boss with this and say, well, here are some heights, here are some volumes. So if trees are around this height, this is what the volume would be. And again, all this is really annoyingly complicated. If we had a linear model, I could just hand him kind of the linear model and say, well, as height increases by 1, the volume's going to increase by blank. But when we do the transformation, this doesn't work. We can't interpret it in the same way, and we can't use it in the same way. It's certainly not nearly as convenient. So it's not impossible to actually make this usable. It's just much more difficult, and the utility is much less. Now I'll say, as I mentioned earlier, that if we had used a generalized linear model and incorporated some of this stuff into that, then in the generalized linear model, R has some functions that can automatically undo the transformation, but it's because we build in the transformations in a little bit of a different way. We actually transform the underlying parameters as opposed to transforming the data, which has some different impacts and is maybe more appropriate. In fact, I have trouble thinking of a situation where it's not more appropriate for the underlying data. So for me, this is what I may hand and say, you know, hey boss, here's kind of a graph looking at the relationship. Here's the data on the graph. Here's this, and you could predict. You know, I could also do a prediction of a whole bunch of different values. I just predicted a few values here, and this makes sense. Again, I got these from the 5-number summary, which is a good description of where these values are, but there's no reason why, if I wanted to create a prediction line, I couldn't come up with a whole bunch of prediction values between 63 and 87. And I'll do this by, let's say, I'll just do it by ones, I suppose. Well, do it by 0.1s. And then I would do this whole process again, and if I did this, I don't want to do points on there because this is going to create a nice smooth curve on my graph, and this would give my prediction curve that I came up with through predicting this particular model. And again, how do we do curves? Well, we do curves because our linear model allows us to do the different relationships. Now, we're not incorporating the relationship directly, and that's one of the things. Recall that when we do transformations on y, what that's transforming is not just the x values and the nature of the relationship. So again, we can do nonlinear relationships with linear models. It's also transforming the errors in a particular way when we do transformations on y, and that was the whole reason that we had looked at that initial transformation on y. One of the things that I note here is this actually looks relatively close to that initial model that I had looked at with the with the quadratic relationship, so taking the square root of y. So it is kind of gratifying to see that that was on the right track at least. And in fact, we might have even chosen that square root of y to make all of this so much more interpretable. Again, this inverse square root of the model really doesn't have an interpretation, but maybe the square root of y would have had a more natural interpretation of the cubed root of y, because white is volume, and again we would have had a more theoretical connection between the height values and the volume values. All right, so as difficult as that was actually the easy example, and it's the easy example because it actually has an answer. Let's jump into a little bit of a harder example where we're exploring some things. So we're going to use the check weight data set. And in the check weight data set, you'll see clearly just from the initial scatter plot of the data, we are going to have some homogeneity of variance issues. We're going to have some huge homogeneity of variance issues. And this should make sense. As baby chickens get older, it should make sense that the variability in their weights get much larger. So on their birth weights are going to be relatively close together because the baby chickens were just born. So if you're consider a baby being born, right? A baby being born, you might have babies that are born, I don't know what baby weights are, but maybe a baby's born at 6 pounds and a baby's born at 10 pounds. They're going to be relatively close together, as opposed to if you look at full-grown adults' weights, where you're going to have full-grown adults who weigh 600-700 pounds, and you're going to have full-grown adults who weigh less than 100 pounds. You're going to have a much wider range of values than you are if you're comparing baby weight. So it's the same thing with chickens, but what it creates is a very, it's understandable, but it's kind of irritating from a statistical standpoint situation where the homogeneity of variance is certainly violated. So we'll go on and fit our model here. Linearity looks roughly fine. It's really the homogeneity of variance. We might have a little bit of an upward slope here that this isn't quite getting. So I'm going to look at the residual plot, again using that plot of the model and picking that first one. So clearly we can see in our residual plot that this is an issue. Looking at normality, it looks like we have a bit of that cubic relationship in the normality. That doesn't look particularly good, so I'll want to keep an eye on that. But homogeneity of variance is a way bigger issue right now. All right, so I've got no idea where to start on the relationship between time and weight. I really don't know. I could try a square root transformation, I guess, but I really don't know. So this is a great time to lean into box plot. Now the problem is I just did my box plot command and I have my 95% confidence interval, and there are no nice numbers in my 95% confidence interval. Oh my gosh. So now what do I do? Incidentally, when this happens, this is usually a good tip. You don't have any theory to guided transformation. Boxcox doesn't really give you much to guided transformation. Maybe this is a good spot to say transformations aren't particularly effective, and for this data, we'll find that to be true. In any case, I'm going to pretend that I can keep going. And what I'll do maybe is I'll say, okay, well, what is the closest nice number to the confidence interval? And it looks like 0 is the closest nice number to the confidence interval. That would imply a natural log transformation. So I'm going to create a variable called ty, transformed y, and that's going to be the log of my y values. And then my tmod is going to be my transformed model, and I'll go on and plot this to see how that worked with my data. Now I see that things widened out at the bottom a little bit, I guess. It's still not great, but it's better than it was. However, now I've got a linearity issue going on because now it's definitely coming up and dropping back down. So now there's a linearity issue that I have to deal with. So again, looking at my residual plot, I can clearly see the linearity issue. And my residuals, I'm just going to say that they're better. They're definitely better, but these are still pretty bad. So better, but still bad. Looking at normality, normality actually looks better, surprisingly. I'm a little more comfortable with this normality plot. Some weird stuff's going on in a few different places, but it doesn't have that deep cut here going for the upward tick. So normality actually does look a little bit better here. Um, what we're worried about now is linearity, and then of course homogeneity variance. It's better, but still bad. All right, so now I'm going to try another transformation. I'm going to try a transformation on x to help with linearity. Now, first thing to note is that if your variable is, if it's possible for your variable to equal 0, then a log transformation, log of 0, is going to break. So if I just type in log of 0 here, I'm going to get some problems. So I have to add a small constant to make sure that the log doesn't break. In this case, I'll add 10. You could add 1. You could add 0.01. There's a variety of things. And now I'm going to fit my transformed model. So now I've got transformed x and transformed y. So I'll do my plot. Linearity looks a little bit better. My residuals still don't look particularly great. But yeah, linearity looks like it's better than it was. Normality looks relatively okay. Kind of looks about the same as it did previously, but certainly better than it was originally. So because my homogeneity variance is still really bad, what then I might look at is for more transformations. And I don't really have a guess, so I'm going to run Boxcox again. Well, running Boxcox again, I see Boxcox now suggests adding an additional transformation between -1 and -2. So the nice number here would be -1.5, and then -2 is kind of on the borderline. So I'd include -2 as a possible option. -1.5 or -2 as transformations. So that is the inverse -1.5. So 1.5 is 3 over 2. That is an inverse 3/2 transformation on y, on top of the current natural log transformation on y, which is also including the natural log transformation on x, and on and on and on and on. So we could do this. We could implement this. We could see if there are still problems. When there are still problems, we can look for more transformations. We can keep going. But honestly, what we're finding is that in this particular case, transformations really are not going to, they're not going to fix everything. And you can quickly see, if we had difficulty interpreting a -1/2 power transformation up above, and we said that's not really possible, what would you do with a -2/3 power transformation on top of a log transformation for that variable y, on top of a log transformation for the independent variable x? How would you even possibly address that? And what you'll find is, again, this interpretation issue is a huge, huge, huge limitation on the transformations that we can implement. From here, I would say that it's not good practice to keep going. What I would say is something like, we had issues, we weren't able to address them via a transformation. Now, this actually is a really good case, and I'll pull up our data plot one more time to demonstrate it. This is actually, I won't call it a simple model, but it's a really good case of using models that actually allow variability to change. And there are statistical models and generalized linear models that allow your variance to go up as your x values go up. So if we used a distribution, such as maybe the Poisson distribution, Poisson wouldn't quite work here, but that's the type of distribution we'd be looking at. The Poisson, as the mean increases, the variance increases. The mean and variance are the same. So Poisson would expect the mean and variance to increase through something what we call the mean variance relationship. So in this particular case, we might look at one of those different distributions that allow for that to happen, as opposed to trying to, again, really nail our square peg data into the round hole of a normal model with a variance that doesn't increase or decrease, that stays constant throughout the model. So in this particular case, even with 2 transformations, I couldn't fix it. Adding another transformation, honestly, we were just going to keep going down a rabbit hole of transformations. Could we find some combination of transformations that fix this issue? Yeah, we might be able to. If we went down, start doing 2, 3, 4, 5, 6 transformations, we might eventually get to a place where the issue is fixed. But again, The questions that we ask are about the relationship between time and weight. And by the time that we've done 5, 6 transformations on one or maybe both of these variables, the relationship between time and weight for all intents and purposes can no longer be studied. All that we can say is that some transformation of time is related to some transformation of weight in some way, and the utility of that relationship really goes out the window. In contrast, utilizing a generalized linear model that simply allows the errors to have different variances at different points, the interpretation is so much easier. It's so much more straightforward within that framework because the interpretation is guided and included in the model. It's not to say that it's necessarily as easy as a simple linear regression. That is to say that comparing this with data that have undergone multiple transformations to fix issues, there's really no comparison. Better models are simply better. All right, for our last example, I really wanted to show you. This came up. I normally don't do this example in this class, but I thought, well, we never really talk about a case where data don't need to be transformed. So what I wanted to do is to create a model with the undergraduate data set looking at how SAT scores predict the freshman year GPA in college students. And what we see here is a nice little data cloud. Looks like we've got some small positive relationship between SAT and GPA, or a small positive correlation. And so in this particular case, we could consider looking for a transformation. Let's say I really thought for some reason that my residual plot was way off. So let's do a plot of our model real quick. And let's see what we have with these two plots. So residual plot, and I've got my QQ plot here. You'll see this is plot 1 and 2 from the default model plots. So there's no issues here. Residuals look fine. QQ actually looks great. So in this particular case, there's really no issues. But let's say I looked at my residual plot and I said, oh my gosh, the variance is increasing, then decreasing. There's huge variance issues here. Or let's say I looked at my QQ plot and said, oh, look how far away these data are from the line. Look how far away these data are from the line. We've got huge normality issues here. And so I determined that I need to use my boxcox to give me a suggested initial transformation. Well, when I pull up my boxcox, what you'll see is that in this boxcox, my 95%, well, first of all, I don't even see the full 95% confidence interval. So I may want to change different values of lambda so I can actually see the full confidence interval when I'm making my comparison. Boxcox has an argument that you can include called lambda that allows you to give it a sequence of values for which it calculates the log likelihood for these different lambdas. So I want to go from -3 to +3. I want to contain more of this interval, and I want to make sure that we calculate at each of the lambdas of 0.1. So 1.1, 1.2, 1.3, and so forth. Doing this, I can see that my curve extends out to 3, and I see that my 95% confidence interval goes out to 2. Now, there are many nice numbers included in here. 0.5, 1, 1.5, and 2. All of these are possible transformations, but I want you to note that 1 is a possible transformation here. What this means is that boxcox is suggesting that it is very reasonable to not perform any transformations on the data. Recall a lambda of 1 is no transformation. In this particular case, where 1 is included in the 95% confidence interval, typically we go with no transformation, unless it's very, very clear from statistical testing of hypotheses. Even then, again, as we've talked about before, I don't particularly trust the statistical tests. But even if it's very clear from plots unless it's very clear from plots that we need to do a transformation, even if it's borderline with plots for homogeneity of variance and normality, or linearity, I would not approach a transformation if 1 is included in the 95% confidence interval from the box plot, because we really want to keep our models as simple as possible. We've discussed in the first example how including even a single transformation can really make interpretation difficult. So when at all possible, I want to keep my variables on the scale to which I was given them. The exception, as always, is if I have a theoretical reason to look for a different type of relationship between my independent and dependent variable, and we've discussed that before. But given no theoretical relationship and given that one falls within the 95% confidence interval of my box plot, I would suggest no transformation of this data. Now, what's interesting, and I don't want you to take the wrong message from here. My message is not, if your assumptions look fine, you have to check for a transformation of the data. That is not my message. You do not have to do this if your assumptions look fine. My message is, if you check your assumptions and you think you may need a transformation, and then look for a transformation, if one is in that 95% confidence interval, consider revisiting those checks of assumptions, because what Boxcox is saying is that they may look absolutely fine. So this is a good double check for when you believe you need a transformation that may occasionally suggest, actually, you may not need a transformation for this data. In this video, we've discussed remedial measures in simple linear regression in R, discussing a simple example which had a solution that we could actually implement, a complex example where we implemented multiple transformations that didn't seem to fix the problem, and an example of where we don't actually need any transformations at all.